This is the 9th in a series of videos that I'm creating to support a number theory course. We just got done talking about congruence modulo n, which built off of the idea of divisibility. And now we're going to use that to prove some nice divisibility rules. So some of these you've probably seen, and some of them might be new. So we want to start with a natural number n that has digits am, am minus 1, all the way down to a1, a0. So that's how we'll write n having those digits. So that means it has the following base 10 expansion. 10 to the m am plus 10 to the m minus 1 am minus 1 all the way down to a0 times 10 to the 0, which is 1. And here the digits are coming from 0 through 9. Again, this is just the standard base 10 expansion. Okay, and now here are 4 divisibility rules that I believe don't require any proof. First, 2 divides n. In other words, n is even if and only if the last digit is even. Notice this last digit, or this ones digit, is a0. So again, I don't think that requires any proof. Further, 5 divides n. In other words, n's a multiple of 5 if and only if the last digit's a multiple of 5. Well, that's also pretty clear, but that really follows from the fact that 5 divides 10. So that means we can just clear all the stuff before this last digit off and only look at the last digit. Next, 4 divides n if and only if 4 divides the last 2 digits. So I've written that as a1, a0 with the line over it. And why is that? That's because 4 divides 100. So that means you don't need to consider any of the digits past the 100th digit. Okay, and then finally 25 divides n if and only if the last 2 digits, a1, a0, come from this set. 0, 25, 50, and 75. So like I said, I don't think these require a proof. Now we're going to do a couple. Let's see, I've got 6 of them that might require a simple proof. We may not do every proof. We may leave some of the proofs for warm-up. So the first goes like this. So again, this one is probably pretty familiar. So we've got 3 divides n if and only if 3 divides the sum of the digits of n. And then furthermore, 9 divides n if and only if 9 divides the sum of the digits of n. So let's see how this proof goes. So notice that 3 divides n if and only if n is congruent to 0 modulo 3. Well, that's just the definition of congruence mod 3 along with the definition of divisibility. But that is exactly the same as saying a sub m times 10 to the m plus a sub m minus 1 times 10 to the m minus 1 plus all the way down to a sub 1 times 10 to the 1 plus a sub 0 is congruent to 0 mod 3. Well, what have I done there? I've really just replaced n with its definition via this base 10 expansion. But now what we can do is reduce each of these guys modulo 3. So let's note that the number 10 is congruent to 1 mod 3. Well, why is that? It's because it's 1 more than a multiple of 3. But that tells us that 10 to the k is congruent to 1 to the k, which is just 1 mod 3. This is going to be true for all k. Okay, but that means our statement up here is equivalent to saying that am plus am minus 1 plus all the way down to a1 plus a0 is congruent to 0 mod 3. And that's because we did this reduction where we replaced all these powers of 10 with 1. Again, from our observation here, which is in yellow. Okay, but this statement is equivalent to saying that 3 divides am plus all the way down to a0, which is what we were going for. I have it written in the other order, but it's obviously the same. Now let's quickly knock out this 9 divides n if and only if 9 divides the sum of the digits. So I can do that maybe just with a couple of changes to this proof. So I can change this 3 to a 9 if I change this 3 to a 9. But that's if and only if this sum, which is just the base 10 expansion of n, is congruent to 0 mod 9. But let's notice that 10 is congruent to 1 mod 9. So it's congruent to 1 mod 3 and 1 mod 9. But that means 10 to the k is congruent to 1 mod 9 for all k. But that means that this line is equivalent to this line because we can do this reduction mod 9. But that ends with 9 dividing this sum. So that's a quick proof of both parts of this proposition. Okay, so let's maybe get rid of this and we'll prove a couple more and then maybe state the rest and leave them for warm-up. So our next rule is a divisibility rule for divisibility by 11. So we've got 11 divides n if and only if 11 divides the alternating sum of the digits. So I've written that as a0 minus a1 plus a2 minus a3 all the way up plus or minus am, really depending on the parity of m. Do we have an even number of digits or an odd number of digits? Okay, well, let's see how this goes. It's going to go pretty much the same as what we saw before. So let's notice that 11 divides n if and only if n is congruent to 0 mod 11. So that's just by the definition of congruence mod 11. But that's if and only if a0 plus a1 times 10 plus a2 times 10 squared all the way up to am times 10 to the m is congruent to 0 mod 11. Again, I've just replaced n with its base 10 expansion. But now let's consider the following observation, which is really pretty clear. And that is 10 to some odd number is congruent to negative 1 mod 11. And then likewise, 10 to some even number is congruent to 1 mod 11. So it's pretty easy to prove this maybe as one of the warm-up exercises. Okay, but what does that mean? Well, that means we can replace each of these powers of 10 with either a plus 1 or a minus 1. So this one gets replaced with minus 1. This one will get replaced with plus 1. And this one will get replaced with plus or minus 1 depending on the parity of m. So that means we can do that reduction. And this line right here is equivalent to the line a0 minus a1 plus a2 minus a3 all the way up to plus minus am is congruent to 0 mod 11. But now that alternating sum being congruent to 0 mod 11 is equivalent to 11 dividing that alternating sum. Okay, let's look at one more proof and then we'll state a couple more and leave them as warm-up exercises. So the next one we've got is that 37 divides n if and only if 37 divides this strange sum that we're taking 3 digits at a time. So we've got the 3-digit number a2, a1, a0 plus the 3-digit number a5, a4, a3, and then so on and so forth until we run out of digits. Okay, so let's see how this proof goes. Maybe it'll be useful to start off with the following observation, which again will help us with this proof. And that is that 10 cubed is congruent to 1 mod 37. So maybe this would be useful to check. But all you have to do is check, well, 10 cubed is equal to 1,000 minus 1 is 999. So all you really need to do is check that 37 divides 999. That shouldn't be too hard to do using like elementary school arithmetic. Okay, but from there, we can just do essentially the same strategy that we did for the other proofs. So notice that 37 divides n if and only if n is congruent to 0 modulo 37. We're going to work mod 37 just like we worked mod 3, 9, or 11 as needed. But that's if and only if we have a 0 plus a1 times 10 plus a2 times 10 squared plus a3 times 10 cubed plus a4 times 10 to the fourth plus a5 times 10 to the fifth plus dot 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 is congruent to 0 mod 11. So I've extended it out like a little bit just because it'll be useful for our case. Okay, but now notice we can collapse these. We can collapse this thing, which is in yellow parentheses, to the 3-digit number A2, A1, A0. So I'll put the line over it to just point out that that's that 3-digit number. Then we can factor a 10 cubed out of this. If we factor a 10 cubed out of this, then this will be 10 to the 0th power. This will be 10 to the first power, and this will be 10 squared. So that's going to leave us with 10 cubed times the 3-digit number, A5, A4, A3. And then likewise, you can continue doing that until you run out of digits. But now we can use our observation, which is again fairly easy to check. Every third power of 10 will just give you 1 mod 37. So that means you can do this reduction, set it to 1. You can do the next reduction, set it to 1, and so on and so forth. So that'll leave us with this statement is equivalent to A2, A1, A0 plus A5, A4, A3 plus dot 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 is congruent to 0 mod 11, which finishes off this proof. Okay, so I'm going to give you guys 2 maybe to prove as warm-ups, and then we're going to move on to an example or 2. Okay, so we've got 2 more. The first one is that 7 divides in if and only if 7 divides the alternating sum of these 3-digit things at a time. So instead of taking the plain old sum, it's the alternating sum. Then finally, 13 divides in if and only if 13 divides that same alternating sum. So like I said before, we can leave the proof of those 2 facts as a warm-up. It follows from essentially what we've done with the proof of those other facts. Now let's jump into a big example. So for our example, we'll find the prime factorization of this huge number. So we've got 35,256,375. So let's maybe start with divisibility by 3 or 9. So let's go ahead and calculate that digit sum. So I'll just write digit sum of n. Well, that's going to be equal to 3 plus 5 plus 2 plus 5 plus 6 plus 3 plus 7 plus 5. So I'll let you guys add those up, but what you end up with is 36. Well, notice 36 is a multiple of 9, but that means that n is a multiple of 9. In other words, 9 divides n. So that means we should be able to divide 9 out of n. You would do that just with like standard long division. I'll show what you end up with. So that'll tell us that n is equal to 9, which I'll write as 3 squared times 3,917. 375. So let's see, that's 3,917,375. Now we want to check, is this thing that's left over also divisible by 3 or 9? We can do that again with the digit sum. So let's look at 3 plus 9 plus 1 plus 7 plus 3 plus 7 plus 5. So when you add those up, you'll see that you get the number 35. That is not divisible by 3, and it's not divisible by 9. So that means there are no more factors of 3. So I'll just write that as no more 3s. Okay. So now let's do the alternating sum on this leftover bit. So we've got alternating sum of the leftover bit. So I'll just notate that as n over 9 because that's what that number is right there. So that's going to give us 3 minus 9 plus 1 minus 7 plus 3 minus 7 plus 5. You might say, well, I did this a little bit differently than the order in the proof of the theorem, but it's really the same. You're just going to be off by a sign. So if you calculate that out, you'll see that you get minus 11. Minus 11 is a multiple of 11. So that tells us that 11 divides our number n, or maybe more importantly, 11 divides this leftover bit. So that means we should be able to divide 11 out. And we can, and we'll get n equals 3 squared times 11. And then after that, we have 3, 5, 6, 1, 2, 5. Before we move on to another divisibility test, let's do the alternating sum on this leftover bit to see if there are more factors of 11. So here we have 3 minus 5 plus 6 minus 1 plus 2 minus 5. So let's see, if you add all of that up, you get the number 0, but 0 is divisible by 11. So that means you can divide another copy of 11 out. That's going to leave us with n equals 3 squared times 11 squared times, so we have 32,375. Now let's maybe bring that up and then we'll finish it off. So far, we've seen that n is equal to 3 squared times 11 squared times 32,375. Now we're going to look at the factors of 5. So in order to do that, I'm going to take this leftover bit, this 32,375, and I'll write it as 32 times 10 cubed. So that's 32,000 plus 375. And then I want to notice that 10 cubed is not only a multiple of 5, not only a multiple of 25, but it's in fact a multiple of 125. So if you take 125 and you multiply it by 8, you get 10 cubed or 1,000. So that's pretty easy to see. So I'd say it's maybe a good call to include that in the divisibility rule that requires no proof down here. Okay, and now we can notice that 375 is equal to 3 times 125. So that means 125 can be factored out of this whole thing. 125 is equal to 5 cubed. So we've got n is equal to 3 squared times 5 cubed times 11 squared times, let's see what we've got left over. We've got 259. Now that we've got it down to 259, it's really just a game of guess and check because at this point it's like quite small. Remember, in order to decide if it's prime, you only need to check up to factors that are of the size, the square root of n. So in other words, we need to check primes 2, 3, all the way up to the floor of the square root of n. I'll let you guys figure out what the floor of the square root of 259 is. That's as far as you need to go. Now I'll just jump to the end. This is equal to 3 squared times 5 cubed times 11 squared times 7 times 37. And that gives us our prime factorization for n. Okay, so now let's get rid of this and we're going to do a couple more examples. For our next example, we're going to find all 3-digit numbers that are 5 times the product of their digits. So what do I mean by that? Well, we've got a 3-digit number, which I'll denote by A, B, C with a line over it. In other words, that is 100A plus 10B plus C. And what we want is this number A, B, C line over it to be the same thing as 5A, B, C. Okay, so the fact that this is a 3-digit number, maybe built into that is that A is not equal to 0. Otherwise, you would have something that is a 2-digit or a 1-digit number. I guess we're not including like starting zeros. Okay, so, well, if A is not equal to 0, then that means that ABC overline is not equal to 0, but that means 5ABC is also not equal to 0. So from that, it follows that A, B, and C are all bigger than 0. So in other words, they are between 1 and 9, given that they make digits of a 3-digit number. Okay, So now let's take this base 10 expansion of ABC over line, and then this rule that has to be equal to 5 times the product of the digits, and see what we can get out of that. So we have 5ABC equals 100A plus 10B plus C. Now let's reduce this thing mod 5. So reducing mod 5, we see that this becomes 0 mod 5, this becomes 0 mod 5, and this becomes 0 mod 5, because all of these are multiples of 5. So that tells us that C is congruent to 0 mod 5. But recall, C is between 1 and 9. The only thing between 1 and 9 that is 0 mod 5 is 5. So now we have C is equal to 5. And now we'll roll that right back into our original equation. So in other words, right back into this equation right here. So we have 25A times B, because remember, C was equal to 5, is equal to 100A plus 10B plus 5. Now we can divide both sides by 5. That'll give us 5AB is equal to 20A plus 2B plus 1. Okay, so next let's maybe move this 20A to the other side of the equation. That gives us 5AB minus 20A is equal to 2B plus 1. In other words, we have 5A times the quantity B minus 4 is equal to 2B plus 1. But now let's notice that the left-hand side is a multiple of 5. That means the right-hand side is also a multiple of 5. Another thing we want to notice is that 2B plus 1 is odd. So we've got 2B plus 1 is a multiple of 5, and it is odd. Well, that only gives us two possibilities. 2B plus 1 could be 5, or 2B plus 1 could be equal to 15. Notice we couldn't have it equal to 25 or anything larger because B is between 0 and 9, given that it makes up the digits of this 3-digit number. Okay, well, from this, it would follow that B is equal to 2. And then I'll let you check that if B is equal to 2 and C is equal to 5, then in fact, there is no solution for A. So that's pretty easy to check. You'll get a solution, but that solution will not be between 0 and 9, or it won't be a natural number, or something like that. Okay, so our next case will be if B is equal to 7. So we can throw that into one of our equations. Maybe we'll throw that right here. And we'll see that that means that 5A times 3, because 7 minus 4 is equal to 3, is equal to 15. But that means that A is equal to 1. So let's see what we've got. We've got A is 1, B is 7, and C is 5. So that means our only solution to this puzzle is 175. Okay, so we're going to do one more example before we finish it off. So for our last example, we want to find all 3-digit numbers that have equal first and last digits that are divisible by 33. So let's maybe go ahead and set our number n equal to ABA with a line over it. So in other words, this is equal to 100A plus 10B plus A, or in other words, 101A plus 10B. Now we'll apply our divisibility rules for 3 and 11. So notice that 3 divides n if and only if 3 divides 2a plus b, because we've got a plus b plus a. Now let's do the divisibility rule for 11, which is the same kind of thing, but with an alternating sum. So we know 11 divides n if and only if 11 divides 2a minus b. Again, that's because we have a minus b plus a. But now let's take these divisibility conditions and turn them into equations so they're a little bit easier to work with. So that means that 2a plus b is equal to 3 times, I'll call it k, and 2a minus b is equal to 11 times L. Well, that's exactly what it means for this guy to be divisible by 3 and this guy to be divisible by 11. Now we'll use the fact that a and b are between 0 and 9. So let's write that 0 is less than or equal to a and b, which is less than or equal to 9. So what does that tell us? That tells us that 2a minus b must come from the set 0, 11, or 22. Well, first of all, it's got to be a multiple of 11. So why is that? Well, it has to be a multiple of 11, and it's impossible to achieve any other multiple of 11 and other than those three using the fact that a and b come from 0 through 9. So now we're just going to run through these one case at a time. So case number 1 is that 2a minus b equals 0. Okay, but that tells us that b is equal to 2a. Now we can plug that into our other equation. So that tells us that we have 4 times a is equal to 3 times k. And from that, it will follow that a is equal to 3 and k is equal to 4. Those are the only possibilities if a is between 0 and 9. And that's because if a were equal to 6 or 9, we could not achieve 2a minus b equals 0 with the allowed values for b. So if we've got a is equal to 3, we know b is equal to 2a, so that gives us an answer in this case of 363. Now, as a bit of a warm-up exercise, you guys should check the other two cases. So let's write that down. Check other cases. In other words, when 2a minus b equals 11 or 2a minus b equals 22, and see if we get any other solutions to this puzzle. And that's a good place to stop.